let's do this problem. So today we have the second problem from this year's JEE. So this is still from I should say where it's from. So it's still from 2025 JEE advanced. Now I'm doing paper 2. Okay. So it's an actually very interesting problem, and if you look at it carefully and nice in a way I'm going to show you to see it, it's a really simple problem. But if you get kind of distracted by also other geometric things that are happening, you can get lost and make some silly mistakes. Okay. All right. So with that said, you should know one thing to do this problem. So this is actually a Gauss's law problem. So it's the application of Gauss's law. So let's just remind it Gauss's law. In electricity and magnetism, if you have studied that. If you haven't studied that, you can't do it. Okay, just period. So if not Gauss's law, just forget about it. This is not doable. So there's quantity called flux of electric field. So it is basically is defined, 3 lines defined as a double integral of a closed surface. So over a closed surface in a space, and you take a electric field and draw take a dot product with this area element. So this is the normal to the area element. So if this is the area in some place, so this is a dA, so normal to that is n hat, and so surface is like that, so there is an inside and there is outside, and the normal goes from inside to outside. That's the orientation of the normal. Then this is equal to however many charges are inside, okay, and they can be totally randomly oriented, and there may be charges outside, doesn't matter. Okay, so this is the charges remain outside and these charges are inside. So this will be Q that was inside over epsilon naught, right? Now if you had a medium, a linear medium, if you this charges this space, charge doesn't have to be in the medium, but suppose you have some charges and then you had a kind of medium which is going to be very going to read over this medium, then this will be modified by the dielectric constant of the medium. So it's going to be modified by epsilon and will be dielectric constant times epsilon naught. So you will replace this with that. So, and K is the kappa is the dielectric constant. Of this medium. Okay. So all right, we are going to make use of this Gauss's law. Let's now read. So if you know this, then you're in good shape. Let's see. So there's some charge Q on the inside. This inside is no charge, and so you have this cylinder. You can say shell. So this is a shell, and there's a charge Q on it. Or if it's a conducting, the charge all is outside of that thing. Okay, it can be a regular cylinder filled in, but there's no charge inside. And then you have a then it says the annular region. Then there's another cylinder, a can, you can say, but this outside is grounded. Okay, so outside grounded. So if this is the plus charges, then you kind of pull negative charges, make it grounded, you know. So there are no charges here, there's charges Q here, right? So then it says this region that we're talking about between these two has a material with a dielectric constant kappa equals to 5. That's that statement. It says consider a imaginary plane, but just a plane in this space. Length is excuse me, length is L. It cuts through here, and a top cross section is shown over here for clarity. So you have the inner radius cut to R, and this thing over from here to here is a distance R. Let's put a charge Q on the inner, on this only. Okay, then we're supposed to find this quantity flux, flux through so electric field will go, you know, from the symmetry. If this is axis, then you can say which way the electric field go. Electric field will start from here, and but inside will be no electric field. It starts from the surface, but it's going to be from in the radial direction outward and hit that, and there'll and then this will be the case in every direction. Electric field will be just in this space. So if I look at a cross section, electric field in some direction, you start from here and go in that direction. So there will be non-zero electric field here. If you look at an electric field that at this point, there's no electric field here, but it's going to go that way. So so we want to find the flux through this part and through this part of the plane, the one that's in here, right? That part. So we want to on that how much electric field is passing through this surface here, and then we want to find from here. Now from symmetry and from the Gauss's law, if you work it out, you know the inside. So they have three regions, region 1 and 2 and 3. So electric field in region 1 is going to be 0. Electric field in region 1 will be 0. We don't electric field in region 2 is not 0. We don't even know what's in region 3. Let you figure it out. Okay, I'll leave that as a teaser. So electric field in this, let's call it A and a B. I'm going to do a straight line from here to here. I'm going to call that C. I'm going to redraw this picture, but let's just stay with it. D and E. So from B, C, D, electric field is 0 there. So the flux through B, C, D part, if you look at this integral through this area, not closed, this is open integral. Electric field through B, C, D plane, there's the length L is down behind there, okay? When you take cross section, there's a length L there. So dot, I'm gonna call it dA vector, okay? Because this is 0, this will be in, because the E1 is 0, this is gonna be 0. So we only need to figure out flux through AB and DE. But the symmetry is that what are the flux through this must be equal to that. So flux through A, B, C, D, E will be just 2 times flux through AB. Okay, so because flux through because this is equal to flux through AB, which is in region 2, and flux through B, C, D, which is region 1, through region 1, and this is flux through DE, which is also in region 2. So this is 0 and this equal to this, that makes it 2 times. Okay, so this must be equal to that from the symmetry, just the way the whole thing is drawn. So we need to figure out this flux and multiply by 2 and see which one of this is correct. All right. So, right, so let me redraw the picture, and so we are, I can make a really big picture. So we have a inner one, outer one. It didn't come out very nicely because we don't need very nice pictures. It will be fine. So this is the O, and this is A, B, and if I draw a line straight through that is C, 90 degrees. And so we want to know what's the flux through this, what's the flux through AB. So interesting thing is, so the electric field is all in radial direction. So some electric field is going that way, and if you, so this electric field will be that way. So you can see in this angle, anything that comes in this angle will go through here, right? So the electric field from here will go through, cut this as well as cut the outer thing, this electric field line. So anything that cuts this will cut the outer line. So we need to figure out now AB is going to same thing as there was D and E, so AF. So and this is on the outer cylinder, so this is cylinder 2 and this is cylinder 1. Okay, so so flux through AB is of this line, okay, this plane is the same thing through AF, flux through AF of the cylinder 2. So now imagine from the symmetry, this 2 pi, so this is going to be equal to angle AOF over 2 pi, flux through the entire 2 pi, flux through the entire 2 pi, and through cylinder 2. Okay, now let's look at a cylinder 2 and imagine a it's open. I mean this is, so in this cylinder is, we can imagine Gauss's law applying to this. So for Gauss's law you need a closed surface, so we'll have this as the part of the surface. There will be no flux through that because no electric field goes in that direction. We are assuming infinitely long cylinder here, although this is a that surface also, and this surface. So this is a closed surface, and so this surface is made up of edge or top and edge bottom and then sides. So this part is just the sides, but flux through the top edge, is 0 because no electric field lines is crossing, no electric field that way, and flux through the bottom face is edge bottom. Okay, so this is 0, so this is a closed surface, so this equal to angle AOF over 2 pi, and this whole closed surface as drawn over here, and this is flux through the closed surface of E dot dA, or this whole thing is the flux through the closed surface. So this is closed surface, and Gauss's law says that this kind of thing, this is equal to Q over charge enclosed, and this surface will be just, we want to have just inside, like this one is this I want to do just inside, because if we're outside and if the electric field is 0 outside, then we are flux there will be 0. Okay, so we're going just inside because we don't want to having to calculate what is the charge at the outer surface. Okay, we just want to deal with the charge in the inside surface. So we can do just a tiny bit under. So this outer surface is just a tiny bit inside. in the medium with a kappa. Okay, so Q over epsilon. So this is going to be Q over 5 epsilon naught. So now summarizing, so answer should be flux through this A, B, C, D, E. So 2 times flux through AB is equal to 2 times angle AOF over 2 pi times Q over 5 epsilon naught. So this is the angle I need to figure out. So I need to put that angle, and they give you this is R. They give you this distance is square root 2r. That means this angle itself will be 45 degrees, right? Just from there, square root 2 and 1 ratio. That's going to be just cosine. Use cosine, and you're going to get pi over 4. And this angle, this thing is 2r. This is 2, and this is 1. So this angle will be, this bigger angle will be 60 degrees. That makes this pi over 3. So this angle we seek is pi over 3 minus pi over 4. So this is pi over, so I mean, maybe I got too fast. You can say A O C minus B, B O C. That's the angle that should this be. And AOC is R cosine R over 2R minus R cosine R squared 2R. So that's equal to pi over 3 minus pi over 4, or 60 degrees, 45 degrees. And because everything is in the pi here, I didn't write in the degrees. So this is going to be 12. 4 minus 3 is pi. So it's pi over 12. So this pi over 12. So you can see that's just simply 2 times pi over 12 over 2 pi times Q over 5 epsilon naught. 2 pi cancels this 2 and this pi, and this 12 times 5 is 60, Q over 60. So that's the answer. Let's see if that's one of the possibilities. Yep, this is the possibility. So C is the answer. Okay, this was a really decent problem, and I would say it uses a lot of creativity in looking at the whole situation. Okay. I will, with that said, I will see you in the next problem. Now, if you wanted to kind of practice more, you can check out my website over here. If you like this channel, please subscribe, and maybe you can hit like button, things like that. Kind of helps with more distribution. Thank you. Bye.